All right, so based on the chapter 4, section 6, we're going to discuss logarithmic differentiation with these three examples that were given in the handout that you gave me. So we want to take a look at finding the derivative of the following functions using logarithmic differentiation. So in order to work with some functions that are called explicit functions in terms of the variable x and y, we now have a way with logarithmic differentiation to find its derivative. So normally, before this section, you were very concerned with just functions of x, and you used the power rule and the product rule and the quotient rule that you learned in differentiation. But now we're going to step it up with logarithmic differentiation. So it just so happens that the first one is a traditional function of x. So y is a function of x. So what we're going to do is, first things first, this f of x right here, we're going to replace it as y. Y equals f of x, which is a function of x. So we're going to replace f of x with y. Y is equal to x plus 1 quantity to the 7th plus the quantity x plus 2 to the 8th and the quantity x plus 3 to the 9th. Now in logarithmic differentiation, what you want to do is you want to take the natural log of both sides. And the reason why you want to do that is the derivative of the log makes things very simpler in terms of when you have very, very difficult functions to deal with. So in this case, you have three functions that are being multiplied together. So if you knew the product rule of three functions, you could do it, or you could derive it, but you pretty much don't have that kind of time. So you can actually just do what we just said, which was take the log of both sides, the natural log. So the natural log of y is equal to the natural log of everything that's on the right, which is this function of x. So one of the properties of, or a few properties, have to come into play to simplify the right side of the natural log expression. So we know that if anything is raised to a power within the natural log, that power then becomes the lead number and is called the coefficient and becomes the coefficient. And also, if you're multiplying these functions together, then it's going to be, in terms of a natural log, the sum of these functions. So in this case, I have these three functions being multiplied, also being raised to powers. So what I'm going to do is take the 7 and drop it down as the coefficient, apply the natural log to x plus 1. And this is also assuming that x is greater than 0. If not, we would have had to throw it in absolute values, but I'm making that assumption for this problem. Because x plus 1 to the 7th is being multiplied to x plus 2 to the 8th, it's going to be plus, because it's multiplication. This 8 then drops down. The natural log is applied to this quantity, x plus 2. Now because these are being multiplied again, it's going to be a plus. The 9 drops down. The natural log is applied to the quantity, and you have x plus 3. So your natural log of y is equal to 7 natural log x plus 1 plus 8 natural log x plus 2 plus 9 natural log x plus 3, the quantities, of course. So the thing about logarithmic differentiation is that you want to take the derivative of both sides. But if you notice, you have this in terms of y, but you also have the chain rule that has to be involved, because the natural log is the outside function and y is the inside function. So we know that the natural log, the derivative of the natural log of whatever's inside, is going to be 1 over whatever's inside. So in this case, I have 1 over y, because y is the inner function. Now to take the derivative of y, we normally did that from regular differentiation. If you take the derivative of x in terms of y, you're given dy dx. Now you can have it equal to the derivative of these simplified natural logs. So again, we use the chain rule. So I have 7 times the derivative of the natural log of x plus 1. So again, the outside function, the derivative of the natural log of the inside is 1 over the inside, which is 1 over x plus 1, but it's multiplied by 7. So I have 7 over x plus 1 times the derivative of x plus 1 on the inside, which becomes 1, which is why you only see 7 over x plus 1. 7 times this derivative times the inside derivative gives you that expression. Same thing with 8 times 1 over x plus 2 times the derivative of x plus 2, which is 1. And then 9 over 1 times x plus 3 times the derivative of x plus 3, which is 1. So when everything's said and done, your differentiation shows 1 over y dy dx is equal to 7 over x plus 1 plus 8 over x plus 2 plus 9 over x plus 3. Now, in order to find the derivative, which is what dy dx stands for, you have to solve for dy dx. But if you notice, you have this 1 over y that's in front of it being multiplied together. So in order to solve for dy dx, we're going to multiply both sides of the equation by y. So this drops out, and then I have y is equal to this entire quantity, which represented the right-hand side derivatives. But if you notice, y, in terms of the function of x, is what we said all around right here, which is the quantity x plus 1 to the 7th times the quantity x plus 2 to the 8th plus the quantity x plus 3 to the 9th. So because y is equal to this, I'm going to substitute the function of x in terms of what y was equal to. So now I have x plus 1 to the 7th, x plus 2 to the 8th, and x plus 3 to the 9th, multiplied by the entire quantity of these sums, or the sum. So I have 7 over x plus 1 plus 8 over x plus 2 plus 9 over x plus 3. So now I have dy dx is equal to, by using some algebra, if you notice, this entire quantity is being multiplied to the first term. So because I have an x plus 1 and an x plus 1 to the 7th here, they cancel out, and I drop 1 power because this becomes due to this becoming a 6 because of cross cancellation. So my first term will be 7 times x plus 1 to the 6th, x plus 2 to the 8th, x plus 3 to the 9th. Now I'm going to multiply this term with the quantity right here. So if you notice, the x plus 2 and this x plus 2 will cancel out. So I'll drop a power of the x plus 2. Everything else will stay the same. So I have 8 times x plus 1 to the 7th times x plus 2 to the 7th because I dropped, and then x plus 3 to the 9th because it stayed the same. Now the third term right here is being multiplied to this quantity thanks to the distributive property. And now I have 9 times x plus 1 to the 7th, x plus 2 to the 8th, and because there's an x plus 3 and an x plus 3 to the 9th, I'm going to cross out, cross cancel, and drop this by a power, leaving x plus 3 to the 8th. So yeah, we can simplify it even more, but to me this is pretty substantial in terms of what this product rule will provide for us in terms of the derivative. I wouldn't go any further than that, even though you could. So your answer is what you have boxed up right here. So that's logarithmic differentiation, and ultimately it's going to be the same for the next two examples. So now again, for part B, I have f of x is equal to x to the second, 2 to the x power, so this is what we call the transcendental function, or an exponential function, specifically an exponential function. So in this case, we don't know a derivative in terms of this. You haven't learned anything like that. So we're going to use logarithmic differentiation to do that. So again, change the f of x to y. So y is equal to 2 raised to the x power. Take the natural log of each side. So I have the natural log of y is equal to the natural log of 2 to the x. As a property of logs, now that this is a power, this is the exponent, and what we do with that is we're going to drop it as the lead coefficient. And unfortunately, the lead coefficient is an unknown. It's an actual variable. So now what I have is the natural log of y is equal to x times the natural log of 2, which we know this is a constant. It's specifically 0.693. So it's a constant. So treat it as if it were like 2x or 3x. So what we'll do is just use simple differentiation now. So the derivative of the left is equal to the derivative of the right. So take the derivative of both sides. So just like we had in the previous example, that the natural log of y, its derivative is going to be 1 over y due to the outside function times the inside function, which is dy dx due to the chain rule, is equal to this constant times x. So if you take the derivative of 2x, you're just left with 2. So in this case, because I have x times the natural log of 2, the x will drop out and become 1, and I'm left with the natural log of 2. So again, I have the funky left, so I'm going to multiply both sides in terms of y. So now I have dy dx is equal to y times the natural log of 2 Now that I know what y is, which is 2 to the x, I just substitute for it. So dy dx is equal to 2 to the x times the natural log of 2. The last one is for part C, f of x is equal to the unknown root of 3, right? So it's a better way to describe it is write it as a fractional exponent. So in this case, the power of 3 is 1 and the root is x. So it becomes y equals 3 to the 1 over x power. So again, take the natural log of both sides and you'll find that the natural log of y is equal to the natural log of the exponential function 3 to the 1 over x power. So again, using properties of logs, we're going to say that the natural log of y is equal to this 1 over x becomes the lead number, or the lead variable in this case, times the natural log of 3. So what I'm going to do is write it as a negative exponent for the sake of differentiation. So x to the negative 1 times the natural log of 3. Take the derivative of both sides. Just like the left, we have 1 over y, which is the outside function, times the inside function, which is dy dx. So again, we have this function right here. So because this is a constant times this this negative exponent, the derivative will be negative x to the negative 2 times the natural log of 3. So now I have the funky left again. So solve for dy dx, so that means multiplying both sides by y. So y is also represented as this function that we said right here initially from what we stated. So we have y times, and I kind of simplified it and threw it back down and as a rational expression. So it's negative natural log of 3, negative natural log of 3. This will go down to a denominator and make that negative 2 a positive 2. So that's divided by x squared. So this expression times y substituted back here gives me the derivative. Dy dx is equal to negative 3 raised to the 1 over x times the natural log of 3 divided by x squared. So from these expressions, these are fairly easy. They can get very difficult, but this is a good start. So based on this problem, these problems right here, your practice exercises are on page 298, 7 through 35 odd, and then it actually summarizes for you how to take care of the logarithmic differentiation. So if you like this video, or if you watch this video and you like it, just hit like and subscribe, and I will talk to you guys later.